All right, so this is part two of a series of videos reading this article from Nanomaterials about microemulsions of non-ionic surfactant. And let's go ahead where we left off was we'd already talked about what the different type of microemulsions are in the Windsor classification. And we'd done some looking at some of the graphs, and we'd looked at what was called the ternary phase diagram. And what we really want to do is we really want to understand more about microemulsions, and you can always find out a lot more about what and why is going on by reading the introduction. So we're going to go back to the introduction in this video and tackle at least some of it. We'll see how far we get. And again, I always like to say we read things aloud. That's, for me, the best way to do it. Then we discuss what we read. If you're reading in a journal circle or a group or with your advisor or a colleague or a fellow student, then you can take turns. But let's start. Microemulsions have emerged over the past decades as a major research topic in colloid science. So microemulsions, we said before, were at their heart water, oil, and surfactants, and sometimes a co-surfactant. And there's much more to say, of course. Colloid, a colloidal or a colloid itself is something that's small enough that it is unaffected by gravity. So these are nanometer scale to hundreds of nanometers oftentimes. And let's see, yes, this is primarily due to their multiple areas of application, spanning fields like cosmetics, pharmaceuticals, agriculture, food, oil recovery, alternative fuels, and catalysis. And I'm going to underline alternative fuels. So those of you who know some of the other work from our group or are in my group and have done this work know that a lot of our refractive index measurements are motivated by the fact that we're trying to do fuel surrogates and understand a lot about fuels. So I'm going to underline those. I'm going to make sure I circle 16 and 17. And sometimes we do this, sometimes not. But let's go ahead and look at 16 and 17. 16's down here. And it says diesel fuel aqueous ethanol microemulsions. So yeah, so diesel fuel aqueous ethanol microemulsions. So aqueous means water. Ethanol means that it's got ethanol in it, of course. And I wonder if something in the diesel, yeah, no, I don't know. Well, we know they're micro emulsions. And then let's check up 17. Because what we can do is, while we're reading this, we can get these other articles. Let's see, diesel engine evaluation of a non-ionic sunflower oil aqueous ethanol microemulsion. So non-ionic sunflower oil, all right, so that must be the surfactant. No, that's an oil, aqueous. I think one of the things I'm having a hard time with is, what is a surfactant? Can the surfactant be the ethanol if the non-ionic sunflower oil is the oil, or maybe there's some overlap? Anyway, I can start looking at getting those articles for future reading, because that is an area that interests us. And oftentimes when you read a journal article, you get more questions and more things to read than you started with. All right, lots of other stuff. In particular, I'm interested in cosmetics and agriculture as well. Although food, yeah, no, there's a lot of reading to do here about microemulsions. Yeah, and there's lots of reasons. So if and when we write our paper or our posters or our presentations, or probably all of those, we will want to look these up and include the areas that are relevant to the microemulsions that we could be making. Okay, microemulsions are nanoscale colloidal systems with high thermodynamic stability. High thermodynamic stability means that they are, and this is bringing in knowledge that I already have, they're thermodynamically stable, which means if you have a microemulsion today, that since it's thermodynamically stable, it's at its lowest energy point. At its lowest energy point means that it will not separate in particular. And so now seems like a good time to bring up the difference between a microemulsion and an emulsion. An emulsion, classic example, mayonnaise, is something that over time, and for mayonnaise it's a very long time, but it will eventually separate. Emulsions, you stir them, and then they become mixing oil and water. An emulsion would be oil and water salad dressing because they mix and then they very quickly separate. Nobody wants their mayonnaise to separate, so they have a much longer lasting emulsion typically. Although it'd be interesting, is mayonnaise really a microemulsion? I've never heard that it would be. Anyway, lots of questions there. But microemulsions are stable. Emulsions are not stable. Or another way of saying it is emulsions can be kinetically stable. Short term, or even quite long term, they exist, but they will eventually separate because the thermodynamically stable version of an emulsion is separate phases. All right. Incorporating at least 3 components, water, oil, and a surfactant. There's a good source that we might want to check out that might be very basic about microemulsions. Often a 4th component is also included, known as a co-surfactant or co-solvent, which further enhances the stability of micelles. That's a good term that we need to know. Dispersed in the continuous phase of the emulsion. Now, let's talk about what a micelle is. There are 2 types of micelles. There are just regular micelles, and a regular micelle would have oil, and then, let's see, last time we drew a surfactant molecule as having a polar part and a non-polar part. And as you do reading on the internet or ask AI, right? What are examples? So certainly a simple example would have, let's just say, what's called a polar head group. And I should say that the polar head group could also be or ionic head group. Or ionic head group. And typically the tail is actually drawn like this as an alkane chain, although it can have some rings on it, and we'll see that. And typically, so this would have a polar head group and a non-polar tail. Non-polar tail. And sometimes if we draw a micelle, you might draw them. It might be a little far apart. Maybe I drew this too big, but that's not too bad. And then instead of drawing this zigzag structure, oh, there's my micelle so far, you might just draw it like that, like a squiggly. And very squiggly. And then the non-polar part would have the oil in it. And the continuous phase would be the water, because there would be water that is continuous. Oh, did we see continuous and continuous? The water would be the continuous phase because there could be another micelle down here in which there are head groups contacting the water. Yeah, and this one's a little bigger, which is not necessarily good. The oil, and just for fun, and they should actually connect, but you're getting the idea. Oh, there's another micelle where this time I've drawn a circle where the edge is between, where the interface is. Yes, where the interface is. Let's go back to our picture that we did last time, where we had a non-polar liquid and a polar liquid, and now the interface is the edge of the micelle. Micelle? I'm famous for mispronouncing words, so I apologize if I'm not pronouncing it correctly. But the oil is non-continuous in this idea, in this version of a microemulsion, because there's no, like the water is between the different micelles. These are generally called micelles. There is another kind called reverse micelles. And in reverse micelles, the head groups are in the middle with the water, and the chains stick out like that. Woo. All right, that's a terrible version of it, but that's the basic idea of what a reverse micelle is. And in a reverse micelle, the oil phase is continuous, and the water phase, or the aqueous phase, maybe we've talked about how there might be salt in some of these solutions. That would be the aqueous phase. And in the end, just so in the back of my mind, where we're thinking is that it really could be nonpolar or more nonpolar for the oil and more polar, not necessarily water, and for the polar parts, the parts where the polar head groups are attracted to. And then somewhere around here, we might say is the interface for this micelle, and then the size of the micelle is here, like so. And yes. Okay, so where were we? We're up here. It says of the emulsion, microemulsion. Another advantage of microemulsions is that they form spontaneously. Ah, I love that word, spontaneously. As the surfactant and co-surfactant, if present, lowers the free energy, love that term, of the resulting nanoheterogeneous thermodynamic system. Unlike regular emulsions, microemulsions tend to be less viscous, visually transparent, and optically isotropic. All right, isotropic is a key phrase from my life. It just means everything's the same in every direction. There are no optically different directions. And that's all we'll say for now. In addition to having excellent long-term stability, since they're thermodynamically stable, which comes from the nanometric dimensions of their micelles, typically below 100 nanometers. And there's some good references to sizes, I would guess. Maybe just definitions, though, of the micelles. Similar to regular emulsions, microemulsions can be oil and water. There's the abbreviation for that, where normal micelles made of oil with a surfactant coating are dispersed into a continuum of water or water and oil. Yes, oil and water, that's the one we've drawn, oil and water. And then reverse micelles are water and oil. All right, so here we are, water and oil, encompassing inverse. All right, reverse, inverse. I actually heard reverse more, but inverse. And that's an interesting thing, because as you read, you might be thinking that an inverse micelle was different than a reverse micelle. But I would guess that they're the same. There's only two ways we can do this, really. All right. With water on the inside of a surfactant shell dispersed into the oil. Yes. Okay. The description tells us that an inverse, well, that we're going to be calling these inverse micelles in this paper and not reverse micelles. I think I had that right. Well, the Windsor classification of microemulsions delineates 4 types of systems. Figure 1, loved finding where they mention the figures. Windsor 1, consisting of an oil in water microemulsion. Here. Phase in equilibrium with a top oil phase. That's this one. Windsor 2, consisting of a water in oil microemulsion in equilibrium with a bottom aqueous phase. Windsor 3, representing an equilibrium between a top oil phase, a bottom aqueous phase, and a middle microemulsion phase, referred to as bicontinuous. I have to read more about that. Which concentrates all the surfactant within intertwined domains of both water and oil and water. Okay, they're bicontinuous. All right, so that's worthy of a note. So this is bicontinuous. Bicontinuous. Can you see that? Oh, there we are. Bicontinuous microemulsion. All right, so this one, let's see. So Windsor 1. Windsor 1, consisting of an oil in water microemulsion phase in equilibrium with a top oil phase. So I don't understand why that is. So oil, water. This one is water and oil. Right, Windsor 2, consisting of a water and oil microemulsion. Huh. Oh, well, so we'll have to think about how they make these, like, because I don't understand why the oil is in the regular micelles when there, maybe because there's excess oil up here. Anyway, I don't understand that. And Windsor 4, which is a single phase that can be either oil and water or water in oil. Oh, there's reference 7 again. The particular type of Windsor system form depends on the relative proportions of components, the choice of surfactant and or co-surfactant, the presence of certain electrolytes, and environmental conditions. So, lots of possibilities for the Windsor 4 here. But lots of questions like why? Why is it oil and water? Why is it water and oil? We'll have to come back to that. Maybe it'll answer them. All right. As a result of their spontaneous formation and high thermodynamic stability, the fabrication of microemulsions is generally based on low energy methods, typically the phase titration method, yay, and the phase inversion method. Oh boy, here's reference 7 again. Well, when you see it that many times, you gotta go see what it is. And you gotta probably get it if you can. 7. Overview of extraction methods, health benefits, and encapsulation delivery using microemulsions and nano. All right, so far we have 7, 16, and I'm just going to circle 17 on the screen camera there. Wait a minute. 7, Chuka, Rakovita, Curcumin. I recognize some of the names. Rakovita, Chuka. Do a couple of the names anyway. Okay, well, so good. They're referencing themselves, and they've done a lot of work in this area. All right, where were we? The former, let's see, the former phase. The former consists of starting with binary mixtures with variable ratios of the 2 components, to which the 3rd component is slowly added, titrated, with minimal stirring. Most commonly, the oil and surfactant plus co-surfactant, if any, are mixed over a range of mass fractions, and the water is titrated in small portions until the respective types of winds or phases are observed visually. It is, however, possible that the oil and water are mixed originally, and the titration is performed using the surfactants. All right, so I'm just going to write down here different ways of doing titration method. And then one of my symbols is that I need to check back is a star, and I'm going to point to these. All right, I know I just wrote over my other words, but hopefully that won't be too bad. All right. Ternary or pseudo-ternary if a are then constructed. Ternary or pseudo if a phase diagrams are then constructed, we're going to want to do that. The various Windsor phase existence domains being delimited by frontiers or Windsor curves given by the experimental compositions where the phase transitions have been observed. And we've seen a picture of that already. Typically, the phase transitions observed with surfactant titration are either Windsor 1, 3 to 4. All right, 1 to 3 to 4, or I'm guessing 2 to 3 to 4. 2 to 3 to 4, it's a little hard to see under there, or 3 to 4. Not all systems will show all of these transitions. For example, the Windsor 3 phase may not be observed, or a system could form the monophasic Windsor 4 from the first drop of added surfactants. Something happened the other day where I added 1 drop of surfactants and it all became one thing. So like a Windsor 4, but I don't know why that was. And that's part of how we ended up here today. The second fabrication method, the phase inversion technique, implies switching from oil and water to water and oil, or vice versa, by one of 2 options. Either the addition of an excess amount of the dispersed phase, right? The dispersed phase is, probably the one that's in there, at constant temperature, phase inversion composition, PIC, or a change, or PIC, I should say, or a change in temperature at fixed composition, phase inversion temperature, PIT. The phase transition is triggered by PIC, and PIC by the modification and fusion of micelle particles upon introduction of the excess components. On a PIT, a decrease in surface tension upon cooling triggers the phase inversion. And so I've just got lots of questions, and this seems like a good place to stop.